All right, for people joining this live stream, we are talking about compiled layers for neural networks for upcoming version 12.2 of Wolfram language. All right, so where have we got to last time? We had stripped out some of the kind of giant dogs being wagged by tiny tails, I believe. But can you?
I'm not sure what you mean by that.
What's that?
I'm not sure what you mean by that.
Well, I mean, there was some whole mechanisms that were giant language redesigns that weren't going to happen as a result of this. But hopefully those have all been stripped out, right? All the things to do with named, well, why don't you go through what you want to go through here?
Yes, so this I think we kind of saw last time, right? So compiled layer, first argument is a function, second argument is a gradient propagator or gradient propagating function.
Let me just see the thing. So the function f is going to be applied to the input, and
what the gradient propagator, actually you can see it in section just below. It's actually it has a wrong name. It's called backward function here, but anyway, same thing. So this takes the output gradient and gives back the input gradient. Okay, that's kind of that's its role. It's propagating in the reverse direction the gradients of the loss.
Is its argument order correct? How can it give back the input if the input is one of the inputs?
The input gradient.
Exactly. The output of this function is the gradient of eventually the loss of the network with respect to.
Okay, but so if this was a derivative function, what you're calling input, which is the point of evaluation of the gradient, would be the thing that is fed in as a curried piece, right?
So that's the input of the function, yeah.
Right. So I mean, if I say d f of x comma x, right, the thing I get is f prime. This thing that you're representing here is supposed to be the f prime, which would have in your notation, that would be something like, backward function of, and then it would say whatever the function is, and then the input would be a thing that was fed to it. Is that correct?
Except backward function also gives you the derivative multiplied by an output gradient.
So yeah, this is where this design we looked at very briefly last week that I had for this adjoint derivative sort of comes in, and maybe it's worth looking at the page I have for that.
Okay.
Yeah, we have a bullet about automatic differentiation there.
So what should I look for?
It's called adjoint derivative.
No, actually, we're not going to use that. So for our
no,
this
I want to see
is the
it.
concept.
I want to
this
see
is the
it.
concept.
Okay, the concept. Fine.
Yeah.
Okay. So, what is an adjoint derivative? Represents delta. What is delta? Is delta an operator here, or is delta a scalar?
Delta's a delta. In this case, in that first one, it's a scalar. In the second one, it's a vector.
Okay, so that says, I don't understand this notation at all. So I would have thought that from a mathematical point of view, this is some kind of, I mean, if you've got a scalar field, f of whatever, or a scalar function of position, what is this? This is some kind of, tangent vectory thing, is it not? Where does this live?
More like a normal vectory thing.
Okay. But does this thing live? I mean, the derivative sort of lives in some kind of tangent bundle. Where does this thing live? What kind of an object is it? Adjoint derivative of delta. What is that?
Delta lives in this output space of the function.
Right. Delta is in the output space. So remember, we had this other definition, and this was done to be similar to this, which is directional derivative, which is much easier for people to understand.
But directional derivative has the direction here of the function, and then where it is being evaluated.
Where it is being evaluated, exactly.
Okay.
So this is sort of, it's trying to make an analogous syntax, but now delta is in the function space. versus the input space.
So why is it in that argument position? I mean, isn't it rather adjoint derivative of f, and then this delta is telling you kind of how far to go in a particular direction or something? Is it a direction? What is it? Explain to me what this thing actually is.
It's a direction in the function space. So it's a combination. It's a combination of the function.
So wait a minute. So you're taking the value and you're saying, yeah, okay, where is the, this is in, no, f applied to x, f of x. What happens with a univariate case? Is there a univariate case?
Yeah, there's a univariate case, but
okay,
it's,
what happens,
you know, consider it as a vector of one thing. Probably the thing that might make it most easy to understand is the third note, which says for a vector valued function, adjoint derivative is equivalent to the gradient of delta dot f.
How can there be a delta? Oh, for a vector valued function.
Right, for a vector
okay,
valued function.
So you do projection of the function in some direction.
Yep.
And then it's the derivative.
It's the gradient of that.
It's the gradient,
yeah,
with respect to the point at which you are looking at the okay, I understand what
precisely. And again, this is just an I don't even think the name is right. The argument order can change. It's the concept I think we really need something for.
Okay, hold on.
This is very helpful, by the way.
So hold on, let me think here. So this is a function dotted into the vector. So I'm sorry, a vector dotted into the function. So in a sense, you're really taking a derivative of, I mean, otherwise this would be a gradient. I mean, just to write this out, this is basically gradient of, and then it's your vec dot f of x with respect to x.
Precisely.
Okay. And for some reason, you want to write this whole thing as a function. Yeah, okay, well, I can see why you're doing it in the order you're doing it. It makes some sense. Okay. All right. So then explain to me how that relates to this backward function here.
Well, because that's exactly what you do in neural networks when you do backpropagation.
No, okay, so I'm saying, yes, so you've got an argument order. You've got, explain to me.
Okay. So the goal of backpropagation is to compute the derivative of the loss with respect to all the weights, right?
Yep.
And so you start from the top of the network, just the loss, and then you step by step compute the derivative of, let's say, of the loss with respect to one layer. And then to obtain the derivative of another layer, of the loss with respect to another layer, you multiply this first derivative. So derivative of the loss with respect to layer n, let's say, you multiply it by, basically you apply the backward function, what we call the gradient propagating function, to obtain the derivative of the loss with respect to the layer n-1. So that's why we talk about output gradient. So this is a direction in the function space, but for us, it's actually the derivative of the loss with respect to the output of the function. And then we compute the derivative of the loss with respect to the input of the function using this gradient propagating function, which is exactly the same thing that Rob.
And what's the output doing there?
The output is a commodity because often, because the fact is, in a neural network, you have the output, you computed it already. And sometimes it's faster to reuse the output. You can express the gradient with respect to the input with the output.
A simple example is think of this for the exponential function. This is not layer related, but the output is x of x. Well, the derivative also is x of x. So why compute it twice?
Exactly. So you at least need an output gradient for sure. Often, if you have the input, it's faster. Actually, not faster. No, if you have sometimes you need the input just to compute.
All right, let's zoom out for a minute, okay? Ethan, our live stream, is suggesting we look at Swift TensorFlow and talking about differentiable languages in general. What does it mean to be a differentiable language? What does it mean? You have a piece of code, and the piece of code in general is some function f of x that has all kinds of stuff inside it.
Yep.
What does it mean to be able to differentiate that piece of code?
Well, that's what I've worked on, last year and this year, is this automatic differentiation.
I understand that. I want to know, given that I have a function which is defined by a piece of code, right? So imagine that we have f of x blank colon equals blah, 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 right?
Yep.
Now you want to be able to compute f prime of x blank in some sense of f prime, and you want to be able to do that by symbolically looking at the code, right? That's what you're trying to do. Am I correct?
Effectively, yes.
Okay. What's the effectively part?
Well, we look at the symbolic version of the code by reducing it to a code graph, which is what the compiler does.
I understand that, but yeah. That's from the point of view of the user. You wrote a piece of code.
Jacobian. It's computing Jacobian. That's the goal, right? The derivative, which is like the derivative of all the outputs with respect to all the inputs. That's a most general thing you try to compute.
Okay,
no,
so we got a function.
We don't try to compute that, actually.
But that's the goal, right?
No, the goal is to get either a forward derivative or a backward derivative, which does not compute the whole Jacobian.
But then you combine them to anyway.
So the goal is to compute the dot product of the Jacobian with either of them.
Exactly.
Okay, let's keep it much simpler than this, okay? This is a thing that says f of x blank colon equals code. And let's assume the code returns a scalar. Right? So then, in principle, we could ask for the, let's call it the automatic derivative of f.
Isn't that just f prime?
It is basically f prime. But this is giving, the issue is, so, the question is, can we compute f prime? Given this definition, can we compute f prime? Right? Now, what would be our language way of representing that idea of computing f prime?
That's exactly what this adjoint derivative and directional derivative things I have are for, is a language representation for those.
Okay, but so how would you actually write it? So let's say I've got f of x blank colon equals x plus 2. Okay, or more interestingly, let's say nest, hash plus 1, ampersand, I don't know what. I'm going to let me be really mean and say something like this. Okay?
No
Let's
problem.
say I have something like that.
That's non-differentiable, but it's okay.
Right. Okay. So let's say something like this, right? Okay. So now what am I going to do? What do I then compute here?
You either compute the adjoint derivative.
Well, I just want to know, what do I actually type?
Yeah. So so let me explain what automatic differentiation does, because it doesn't compute the whole Jacobian. It computes either a directional derivative, which is called the forward mode, or it computes this adjoint thing we've been talking about, which is called the reverse or backward mode. So it avoids compute. So you can do one of those two things. Now you can compute the whole Jacobian by applying it a bunch of times, but that's not typically what.
But we're not talking about Jacobians here. We've got a scalar function. So just tell me. Yeah. So what is?
So you can use either. So one way to do it. There are two ways to write. One is adjoint derivative.
I'm not liking this already. Yeah. I'm not liking this. This is I just want to do a very simple thing. I'm taking this function f of x blank. I want to find its derivative using automatic differentiation. How do I do it?
Right. Adjoint derivative of 1 of f of whatever x you want to to apply it to.
Okay, and then what this is going to give me is some automatic differentiation function, some interpolating function like object that, I mean, this would give me some interpolating function like object. Is that correct?
Well, the only case we can do it for is when it can be compiled. So it would be a compiled code function object.
Okay, all right, okay, fine. So, but the case we can do it for is a case where we can get a symbolic result. Is that correct?
No. I mean, it's where we can compile. I
don't care about compilation. I'm saying, I'm asking the question, if I feed in, if it's done with compilation, what is it computing? It's computing a numerical approximation to the derivative. Is that true or not?
No, it's exact. It's
okay,
exact.
So then you didn't answer my question. Then okay. So hold on. There are many different things going wrong here. Okay. Whatever we can do with the compiler, we could do with code. We can do with code transformations. If it's an exact symbolic result, whatever the compiler is doing is also something achievable with code transformations. Is that not correct?
I'll let Tom comment on that.
It's obviously true. I mean, from what you just said, it's obviously true. You make an execution graph, code graph, yes, whatever. It's obviously true. Right? Tom, do you want to comment on that?
I'm hazy about that.
Okay, so I'm not hazy. It's either true or what you're saying is total nonsense, right? It's in other words, this is not a magic numerical scheme. This is something where you take the code graph. I mean, let's take the most basic.
Yes, it is. It is a code transformation.
Right. Let's take a very basic
lambda, case. What the compiler is giving is effectively is equivalent, isomorphic with a lambda representation, a pure lambda.
Right. So then why don't you explain to me in the case of, I mean, a trivial lambda is trivially differentiable, right? So a lambda gets non-trivial when it has conditionals and things like that in it, right?
Right.
Okay, so we can perfectly well take something like this. Does D work for inactivated things? Well, doesn't really matter. If x is greater than 0, x squared, otherwise x cubed.
Well, that case is much easier than the other case you had with something like nest.
Of course it is.
Now,
right.
way back when, Stephen, this is when I worked on derivative, D like 10 years ago. I wrote there's a system option which allowed you to do this symbolic automatic differentiation. And it hasn't been maintained, so it doesn't really work anymore. But it's exactly the concept you're talking about. But it could only handle pretty simple things.
Okay, but so my question
is the full code graph.
Okay, so I understand that. So given the code graph, I don't understand what isn't just symbolic transformation of the code. I don't see why it has anything to do with the compiler. I mean, other than the compiler happens to have code in it that can do the relevant analysis.
Because the way it's written, it uses this single static analysis. What is it? SSA.
Single static analysis.
Yeah, or assignment.
Okay,
right?
Single static assignment. Sorry.
Yeah.
Right.
And so when you
that is equivalent to a lambda representation.
Yes,
so,
fine. It's an immutable thing that is just right. That's the point. It's not doing. It's unrolling it to the point where you don't have variables. Correct?
That's exactly correct.
Yep.
That's 100% correct.
Right. So if you could write the thing in terms of combinators or pure lambdas, then this is a procedure for giving you the derivative, right?
That's correct. I believe
so,
that
yes.
that's a good statement.
Okay, so then in principle, your compiler code should allow one. We could use the analysis code in the compiler to take any expression that we have here and write it in this static, immutable, combinatory form, correct? Must be true from what you're saying. It must be true that I can take that expression, nest or whatever, and I can write that in this as something involving immutable combinators.
Yes.
Right? Okay, so we could explicitly generate that symbolic form if we wanted to. Am I making sense? Right, that must be a part of the pass, some pass of the compiler must do that. Right, Tom? Is that correct, Tom?
I'm sorry, that is a non-trivial question. In some abstract sense, yes.
Okay, well, so I'm telling you, it must work, because the fact is, in the compiler, right? The question is this: there is a trivial sense in which you can do this. You basically write nest in terms of combinators, right? You can clearly do that, right? It may be a big messy thing. Then your challenge is to simplify that expression, as best you can, to make it, and that is a pruning that will depend on type analysis and depend on various kinds of analyses and theorems that you can prove in the compiler.
Well, typically the type analysis is done first.
Yeah, but that's just a convenience. It doesn't matter, right? Yes, that probably avoids you making a very bushy tree that you don't need to make. See what I'm saying? I mean, right? Okay, look, you guys are going at this a bit the wrong way. I'm sorry. This is too muddy. This has nothing to do with the compiler. It has nothing to do with numerical analysis. It's a symbolic transformation of a symbolic expression that we have, and we have great tools for manipulating symbolic expressions, which for some reason we're choosing not to use because we've learned automatic differentiation from people who don't have those symbolic tools, and so we're very confused. That's
Perhaps.
my summary.
I've thought about symbolic differentiation using our symbolic tools, and it's not. I mean, I have a prototype I wrote that uses symbolic stuff, but it's
right.
It's very simple. It's very slow. You get expression swell. You get lots of problems.
Right. Okay. So then the question is, go ahead.
I mean, the result of the automatic differentiation, is a program that computes derivative, but the way this program looks, I'm not sure we are in agreement when you say expression. Like it's not a classic symbolic expression.
What is it?
It's first. I've imagined that a program, the trace of the program is always different. It can potentially be different when you run it. So
what is the code? What does the code look like?
I think it runs the program.
I don't care about running the program. Got asking what the code is.
That's what it does.
Code.
But the code, what's the algorithm? First, run the program for sure. Then it remembers a trace and every internal value of the program during this trace. And then it goes backward to compute derivative of everything with respect, output with respect to everything, and come back. That's what it does.
Yep. Okay. So for many years now, by many I mean 40, I have thought about this question of how do you store symbolic execution traces? Right, we have a function called trace that tries to do that, not very successfully. Right, what you're describing is, what you need to do though, realistically, is not just run the program once, but run all possible versions of the program with all possible branches. Because in general, to make a piece of code that allows you to have these, to have the derivatives taken, right? You need to do all possible branches of the program, don't you?
No. See, that's the whole thing. That's the beauty of this single static assignment thing. It allows us to use these phi instructions that are in there to handle each branch sort of on its own. So we effectively differentiate each branch of that.
So you're saying, given a particular input to the program, you're asking, right? So given the particular input, the program runs in a particular way.
Yep.
Okay, so let's zoom out for a minute, okay? So you're saying your older effort was given a program in general without constraints on its input. What can you symbolically do to define the derivative of the program, right?
Right.
That's thing number one, right? Mm-hmm. Now you're saying thing number two is, given a particular input for a program, what you want to do is make small moves around that particular input, finding in effect the derivative of x plus epsilon, x minus epsilon. You're effectively trying to find those derivatives around that value, correct?
Exactly. And that's a key thing of the automatic differentiation, because if you try and represent the program as the whole thing, No, I
understand. But the point then is, what you're trying to do is to compute that rather than computing x plus epsilon, x minus epsilon, finding a finite difference.
Right.
You're trying to compute it. Why do you save more than a factor of like 3 or 4 by doing this?
Because the number of inputs. Let's say you have 100 inputs. You'll have to do some epsilon on the 100s of them.
Okay. All right. Fine. That's a good answer. Yep.
Right. Yeah. And
okay.
And there's also other ways this can be used, this adjoint derivative concept. So for both ND solve and this parametric optimization we talked about last week, there's this concept of getting the gradient with respect to all parameters. We don't have a way of expressing that now. And for, say, a FEM solution with 1,000 degrees of freedom in the initial condition, you want to find the sensitivity to that.
Okay.
You need this concept.
I get it. So let's walk through the concept that you have here. Okay. So what you're saying is we got a function, and the function in general has a whole vector of inputs, right? Which could be 100 inputs.
Yeah.
Right. And what you're saying is you want what you're asking for is essentially, I don't even know the mathematical notation for that, is sort of the full derivative with respect to all possible changes in V.
Yeah, but that's the gradient, right?
Well, if this is a scalar valued function,
that is the gradient. Yeah.
Otherwise, the Jacobian.
No, it's not.
For a scalar valued function, it's the gradient.
Right, but in general, it's Jacobian.
In general, it's no. See, what you want is not the full Jacobian, because that's typically impractical to compute.
No, but that depends on your application. It's I agree that to compute for optimization, which is the case we're interested, it's always a scalar function. So indeed, the internal the internal layers for us, we don't want to compute Jacobian for them. It's impractical. You want to backpropagate and never have to compute a new Jacobian. But you could have a function that has 2 outputs, and that's the goal. That's the
yes. Well, you can always compute that by finding the 2.
Right,
with this adjoint, you can find the adjoint in the direction of the first component and the adjoint in the direction of the second component.
So the point is that the functional that we have for derivative is with respect to a particular slot. I mean, what we're doing with derivative 1f, right, is taking, but now that slot with our derivative here, we're not actually committing ourselves to whether that slot is a vector value or not, are we? I mean, we've always done this. We've always imagined that this is a scalar computation.
Oh, but try if you do D, I'm trying to if you do, say, D of F of list of X comma Y comma X, look at what you get.
Okay, so this is a derivative. So in a sense, what you're saying is it's an all up there. What you want here is something which represents not just this, but all possible unit vectors here, correct? That would be the gradient, would be the list of all possible choices of unit vector here.
Yes.
Correct?
Well, yeah, but it's a combination of, right? It's the
Why
vector.
is it a combination?
It's the vector for all possible. So
that's what I said. It's a list of the results for all possible unit vectors.
Yes, that's correct.
Okay. So I'm wondering, and you could imagine, so in a sense, this thing, what is the right name for it? It is almost, the full derivative of, and then it's asking for the dimension D. It's saying basically what you want to do, and where do we have a notation for this? You're saying on that dimension D. I mean, this is the collection of unit vectors here, right? Do we have another function that has a notation for something where we are? Yes, it's basically selecting. It's like part selection where we're just taking a list. It's like array at that point, right? Because what array is doing is it's taking, this thing here, and what we're doing here, what we need is something which is then going to return Yeah, I mean, you need to have it be more general because it's got to be able to do a derivative with respect to the first argument of this, which can have many different pieces, second argument, and so on. Is this making some sense?
Right. That's, yep.
Okay. So now what you're saying is,
what happened? I think the second argument of D, you can put several things, right? And like in a list or list of lists.
no, that's something different. The list of lists I'm not sure about, but a single list is differentiation of. Yeah. Okay. Great. So that's that. So that is indeed the gradient vector.
Yes.
Okay. All right. So then what we need is, okay. And what you're saying is, given a program, you can go through in that program and you can, assuming that the program doesn't assign values to variables, assuming you've managed to make the program one that is sort of enough combinator-like that it doesn't do that, then this thing is purely function composition. So then every individual sort of variation as you go through the program is composable. It's like chain rule. Is that right? Because it's essentially function composition. Am I right?
Yep. Yes, it is effectively the chain rule. But to see, the thing you compute for that for every possible input is for scalars. You can compute those values for scalars. Okay, so if f has multiple components, you need to make that into a scalar to be able to do that. And that's where that delta I have comes in. So you take that combination.
Yeah, I get it. But I mean, that seems to me a detail of you're taking. I mean, okay, you're trying to compute the scalar because ultimately you are writing the innards of your function in the form, f of g of h of whatever it is, right? Where the fgh could be things that have ifs in them and all kinds of weird stuff.
Yep.
Right? Okay, so then, and ultimately what you're doing is you're just computing this thing here, but you're doing so by okay. And the final function that you get going through all of our, system functions and so on, is it representable in terms of symbolic things that we have? Or is it something where in the end, in other words, let's say one of those FGH was some weird hypergeometric function, right? We would presumably compute numerical derivatives of that weird hypergeometric function unless it was, exactly evaluatable.
Well, see,
Am I correct?
Right, but it's possible. See, so for some weird function like hypergeometric function, it's possible that if we could attach a definition of adjoint derivative to that, or whatever we want to call this concept.
No, it's not an adjunct derivative. It's just the frigging derivative. For by the time you get down to an individual function here in the stack of things that represents the thing you're trying to compute, it's just a derivative. I mean, if it's a 7-argument hypergeometric function, okay, there's some special cases there. But basically, by the time you're down at these individual functions, I think it's just a derivative. There's nothing to do with it.
If it's a scalar function, yes, if it's a scalar function, it's just the gradient. Or the forward, the directional derivative.
Right, but so the thing I'm saying is, Sandra on a live stream is pointing out that what I'm calling full derivative, if it was instead of a list, it was a sum, it will be the total derivative. That's correct. I mean, this is a generalization of total derivative, so to speak, to be able to, in a sense, apply an arbitrary function to collect together the individual directional derivatives, basically. When I say directional, I mean on the coordinate directions of the vector, which is not obviously what you mean by a
right. Well, see, that's why I have this other thing I call directional derivative, which does the sort of this other thing. It actually does compute the directional derivative, but it uses a slightly different technique to do that.
Okay, let's zoom out for a minute here. Okay, so what we're trying to do, the general thing we want to do is, given a piece of code, we want to be able to represent the, given a piece of code and a particular input to that piece of code, we want to find the derivative of that code near that piece of input, right? That's the final thing we want, correct?
Typically in a particular direction in the output space.
Well, if the output is a vector, yes. If the output was a scalar.
Yes, if the output is a scalar, that's exactly what we want, Steve.
This I think, for our application, yes, because we're only interested in functions that have one. In the end, we're only interested in optimization, and so in functions that have a scalar. But I think there are other applications where they also care of having the Jacobian. So sorry to say that again, but I think.
Oh no, yes, the full Jacobian is useful, but in many cases it's not. So suppose you want to find the derivative. Again, I'll go back to ND solve, parametric ND solve. So suppose you want to find the derivative with respect to, say, an initial condition for some PDE. Okay, you're not going to practice. Getting the full Jacobian may be, a 10,000 by 10,000 matrix.
Okay, so let's just parameterize what we're talking about here. Okay, so this is. Okay, so what we're saying is that what we want, let's call it, just for now, let's call it AD of a function f at a particular position, right? At an input. So the first thing we want is just this, right? Where this is going to give us something which has the same dimensions as that input space, right? Assume it's a scalar function.
Yeah, so if you, that would be reverse automatic differentiation.
Why is it reverse?
Well, there are two different types of automatic differentiation. There's a forward and a reverse.
Okay.
The forward computes the directional derivative. The reverse computes the gradient. Okay,
so this is backward.
I mean, it's an implementation, right? It's because it's faster. Because in that case, your function is a scalar. It's always faster to apply the chain rule in the backward direction, starting from the output to the input.
All right. Okay. So this gives. So in this case, we're gives the derivative of f at input, right?
Mm-hmm.
Okay, so now there's a different case, you say, which is the forward case, where you're saying we are given the output and the input, presumably.
You're just given the input. So
okay, so what do I do now? So I've got this thing.
AD of f of input. Okay, and then there's some direction.
Direction in the input space.
In the input space, exactly.
Okay. Okay, and then what do I do with that direction?
That it gives the directional derivative in that direction.
I see. Okay.
So the Jacobian dotted with that direction.
Okay, so directional derivative in a certain direction.
Right. And that's simpler than the backward automatic differentiation in that it can do it. It does it in one pass. So it basically only costs twice as much as the function evaluation.
Okay, so
itself.
this particular thing here, this one here, so so case one, okay, so look, case one is returning so let's enumerate these. So case one, returning a list of the same shape as the input. Okay.
Yes.
And then case zero, which is the full Jacobian case. Return a list which is the outer product of input and output. Is that correct?
Yes.
Okay, case three. So this is case two, rather. is the case where you are
it's returning a list the same shape as the output.
Right. Uses, okay, takes dots a direction into the input, returns a list of the same shape as the output.
Right on.
Yeah.
Okay.
And I assume case one is the same, but with the transpose of the Jacobian, right? And like you dot on the other level, no?
Well, okay, so this one here, we could, for a vector valued function, could think of this as dotting with a fixed vector, with a vector against the output.
What's actually, yeah. Yes, right.
That's interesting. There's a mention of a chap called Conal Elliott, who was an employee of ours a long, long time ago. I have no idea what's happened to him. It says he's working on machine learning from the perspective of typed functional languages. It's interesting. Should look at what he's done. He was a bright guy, a bit theoretical for what we were doing 30 years ago. Okay. All right. So in any case, these are the cases we're dealing with here.
Right.
So now each one of these needs some kind of design, and maybe they need the same design. But the way these work, you say, is you're unraveling, you're representing the code in this essentially combinator form. And I don't know whether the compiler could emit, as part of its intermediate code, could simply emit that combinator form. Can it? Tom, Christopher, anybody? You comment on that?
I mean, it can for sure. It's quite limit. I mean, it needs type analysis to sort of run this, and it needs access to all of the functions. So like your floor case, I don't quite know how it would, unless it knew that floor was,
No, but so I'm walking through the goal. The goal is, if you can represent this thing as f of g of h or whatever, right, as a pure functional composition story, right, then automatic differentiation is straightforward, right? So the question is, can you represent things in that form? And the answer is, you have to do type analysis to know whether that will work. Right? So given a particular type, so this is going to be a function that has a certain type, that has certain types of input, certain types of output. And then the question is, can you write it in that form? Because you don't need to use, I don't know what you're doing with the innards of the compiler, but most of what the compiler does, generating LLVM code or something, is irrelevant.
Generate Wolfram language code out of it. That would be very interesting.
That actually would be interesting, Tom.
I mean, that's totally fantastic. I've often wanted to do that.
Okay, so fine, but let me just understand what the objective would be.
Pretty frigging weird, though. It might just look like a big goddamn mess of lambda functions.
That's fine.
Maybe with lambda constructs that we don't have, like let rec, for example. What
do you mean we don't have it? Of course we have it. Right? What aspect of that do we not have?
Actually, we could have a with. We don't have a let rec. So
what does that do?
Well, what it does, it would be like with, where the bindings for the variables were available in the right hand side. That it would be like with recursive. That would be useful, actually.
Okay, sorry, do you mean vararg with, or
no. Like how would you write a with function?
No, all you're saying, Tom, is this. You're saying that the bane of all lambda calculus, everything like this, is that you ultimately need to name variables in order to not be confused about what's happening when you go through nested functions.
Well, yes, except you have this sort of cop-out thing, which is that, these combinators, Y or W combinators that implement recursion without giving things names.
Absolutely.
The wonderful theorem. Now, another slightly weird thing is, I don't think these combinators can be typed, but that's another.
No, you can type them. You can
No,
type them.
not the recursive. Well, you need infinite types.
Right. The combinators are themselves, the symbolic expressions, which are the combinator expressions, have to be included in the type calculus.
But these combinators for recursion, they have to have infinite types. It's like,
no, they just have to have a type schema.
This is a function that returns.
No, they just have to have a type schema, same way you would make an axiom schema. And I'm sure there's a way of thinking about it in terms of, just like you can do higher order logic to think about quantifying over functions. I'm sure you can do the same.
I think they'll be getting off topic, and I'd love to.
No, Tom. The important difference is
Simon Peyton Jones at great length on this, and
right. Well, I think you will find that you can do it using a type schema, which is directly analogous to an axiom schema in axiomatic theories. Okay, so for example, induction, okay, which is the analog of what you're talking about. The induction axiom of Peano arithmetic is not a finite axiom. It's an axiom that is essentially a generator of an infinite class of axioms. But in fact, Jonathan just did this in our theorem prover, is to turn that axiom into a single higher order logic axiom by quantifying over functions. And I'm sure you can do the same thing here. And yes, that is a slightly, that's slightly fancy and abstract. Right?
I mean, the type system, the compiler is first order logic. So you just get one level of type for all. There's no nesting.
I'm aware. But what I'm saying is in order to do what you are describing, I'm pretty sure you have to go to second order logic.
Right.
And there is surely a type analysis.
Not many languages have a second order logic. So that would be let recursion in. Sorry, fine. I'm rambling a bit. Let polymorphism in function arguments. That's that. Like Haskell, I don't think there's any variant of Haskell that does that, for example. But yes, it would be very interesting to generate to generate some sort of Wolfram language output from our intermediate language. I think that would be super interesting.
Right, but so I'm just trying to understand. Okay, so let's zoom out for this meeting for a second. Okay, so to what extent we're trying to put something into compiled layer for version 12.2 that represents some kind of automatic differentiation. It is going to be a hack because we don't understand this properly yet. Right?
I mean, for 12.2, we won't have automatic differentiation. It's you have to specify this what we call gradient propagator, which is this directional derivative.
Okay. Do we know whether we're specifying the right thing here?
I think so. So in terms of the function, the argument, the order of the arguments. So our logic is that the output gradient is always needed to compute the input gradient. Input is almost.
Let me make a suggestion. Let me make a suggestion for kind of defensive design here. Okay. Let's make the second argument to compiled layer be something like, whatever you want to call it, gradient, propagator, arrow, whatever your function is. Okay? Because if it turns out, I mean, I don't know whether, if it turns out that this, and you can say, in general, that can be an association because it might need other parameters in it, but you can elide it to not have the association around it.
It's very, very, very standard. That's how every framework are created that are lower level than ours. You define your backward propagation.
Listen, we will end up throwing away compiled layer.
Yeah.
We will end up throwing it away. So you can take it, you can make a choice. Either compiled layer is a throwaway, or you can defensively design this piece of it. I don't really think this is a high cost, because I think that this is, this is a complicated thing to write anyway.
Yeah.
Yeah,
but it's okay. I mean, look, I don't think compiled layer will survive anyway. So, I think it's useful for right now. I think that there'll be a bunch of things that need to be changed about it. And in fact, I suspect that the very concept of compiled just doesn't make any sense, because any layer, in the end, this will be a custom layer or a function layer.
Yeah, we have function layer. Function layer will probably use
all right, well then
layer.
fine.
I mean,
have this be an experiment thing. You can have it work however you want.
Okay, cool. I think it has some nice thing. I mean, it's really because we have compiled function, and the fact that you have the rank specified in the function that are ready to be compiled. This helps us a lot because we can, for example, we don't have to specify if this function needs to work on a single example or on a batch of example. We can infer it. Anyway, there's a bunch of things that are.
So given where we are in the development cycle, I assume you've already implemented all this stuff.
Yes. Matteo has something running in the last version. Just this last thing, automatic batching, that we need to do.
Look, I'm telling you, make an association of CRUD that you're going to put in here. You're going to need all kinds of things here. Just put in an association that has all these kinds of weird options. There's no way we can do this. This violates.
I don't think we're going to put it. I don't think we're going to put this batch thing. Yeah, it's something that. Yeah, I don't think we're going to put it. This is. We don't need it.
Okay, fine. Then let's not discuss it.
Yeah. This is This is for later, to have multiple ports.
Okay, that's a different. Multiple ports. I don't even understand what that is in terms of what we've been defining up here. Let's review again what we're doing here. So I think I understand this better now. This is a very nice thing which we should have. And
in some sense, thinking about it a bit more is the argument, I'm not sure I have the argument order in these design ideas, but part of the directional derivative came from discussion with Jose, which is why I use that analogous analogy. Because
well, yes. I mean, I understand why, coming from the tensor calculus point of view, I understand why you would end up with that.
And I think having something that would effectively give the full Jacobian is a reasonable thing, but I think it should perhaps be a different function.
Look, I think the right answer here, which we don't have yet, and it's going to take more design grinding, is there is a design which gives the full Jacobian, and that design elides down to cases 1 and 2 when it has a slightly simpler input form. That's what I think. I think it's a single thing that does all of these cases, and that it's simply elisions that give the cases 1 and 2. That's what I think. And I think that the way to think about what's happening inside is, to be able to write, I think it'd be a useful thing, just like in Boolean algebra, right? We have, if you look at Boolean minimize, okay? If I say, A and not B or C or something like this, and I say, and I don't know all these things, but I say, what do we have? I thought we had a BDD, or is it Boolean convert? Let me remind myself how this works. Oh yeah, A and F, for example. Okay, so what this is doing is this is essentially a simple compiler, right? This is compiling into, XOR and AND type format, right? And what effectively we're saying is what we want to do here is, which is rather interesting, is to take a piece of symbolic code and compile it into something which is this single assignment, aka immutable, aka combinator structure. And to do that, I think Tom is probably right that we will end up having to have him. We're just introducing these combinators for version 12.2. We're introducing the traditional Schoenfinkel combinator structure, but that gives us a pattern for, yes, we may need, that actually gives us the ability to do certain kinds of variable, recursive variable binding type things.
I think it might just be a with recursive. Actually, might be sufficient. I haven't, you know, but with recursive would be useful.
What would it do?
Well, right, with recursive, right, and then you do like parenthesis f equals function.
What?
Write this. Okay, f equals function, and then bracket x, comma, in the body of the function, x, comma, then like if x equals 0, you know, 1, yeah, comma, x times f, x minus 1. Right? Okay.
Yep.
And then close the thing, and then comma, you know, f of 20 or something. So this is different from with because the bindings are available in the right hand, you know, available as you make them, you see. So that is like.
Hold on. That wouldn't work with, you're saying.
No, you can't do that with because with f, the binding for f is not available when you make the binding. You see, yeah, right. I'm pretty sure that's like let rec that.
Yeah, it is.
A lot of Lambda languages add sugar for these things.
But I don't know why.
Because writing these combinations
hold on.
Right.
If I were to say this, right? If I were to say module here.
Well, but module's not. Yeah,
No, that doesn't work either. So hold on. What do I need to do here? So I'm just
well,
saying, that's one pass. What are we doing here? No.
Hang on. What you could do is write module parenthesis f, close the assignment after the parenthesis after f before the.
Oh, sure. Then if I say this, and then I say that semicolon f.
Right, and that works. I think there's a comma missing. Right. So actually, the compiler compiles that specially. So it recognizes it sets up the binding. So you can actually compile these things, which I think, and it can do type inferencing for these things. But it would be much neater.
Hold on. What you're saying is, and this is interesting, and I probably thought about this like decades ago,
Sure.
Is the question of whether there is essentially, because what with is doing is this sort of one pass semantics, and whether there is a way of doing this. Yeah, okay. So this is
lambda is just like applying a lambda, is defining a lambda.
I know.
That's what it is. So it's just a different way of writing a lambda function. And it has the same scoping rules and everything, you see. So I think this with recursive would be kind of useful, actually. And yeah.
I think it's not quite the correct design, but I think there is something like this that would be useful.
But fine.
I'm trying to understand what. It's not okay. All right, fine. So that's part of the story.
Can I say another thing? There might be another form of module where you can only make one assignment to the variable as well. You have to make one assignment, but you don't have to put it in, because actually I mean, it's nice to sort of scatter these assignments throughout the function.
Well, the issue is why it doesn't work to do this. Oh, sorry, why it doesn't work to do this, which is a little bit unobvious to me, why this doesn't work.
Because it makes the assignment, because it doesn't apply lexical.
Because it is a lexical thing, which lexically does this.
Yes, right, correct. Right. Yes.
On the other hand, if I were to do this, it's hunky-dory.
Yeah.
Right?
Correct. But we hate block.
This is a more complicated issue. This is not as simple as you're making it out to be.
Okay.
This is, I mean, okay. Again, question. So point of view of, okay, this is discussing automatic differentiation in the perspective of category theory. Yeah, recursive neural nets, recurrent neural nets. How does this all work for this? Good question.
Well, you unroll them.
Yes.
Then you backpropagate through time.
Right. Okay. So I think Richard on our live stream points out interesting case, which isn't often dealt with, is gradients for infinite impulse response filters. GPU optimization for which involves using K Fibonacci sequence corrective terms, which are derived by hand. Okay, so this is, Rob, back in the day when you were deriving Runge-Kutta
Yes.
whatevers. This is that whole story again.
Mm-hmm. Well, see, that's partly what, I mean, I want to mention that's something I want out of this design we come up with, is we have a way of attaching rules to functions that allow you to define these so that some process, compilation or whatever, would be able to find those definitions. For example, you can define a backward rule for linear solve. And so you can find the derivative with respect to all the components into a linear solve using these
Okay, so
rules.
just to make a general comment. I mean, the good news is in our language, there's a ton of stuff that we already do without assigning values to variables. Some things implicitly assign values to variables, like sum, for example.
Mm-hmm.
But mostly, we're not, most people who are worrying about low-level languages and automatic differentiation, their code is just full of assignments. We do not have that issue. And so it should be easier for us to write the code in this essentially combinator-like form. And I'm a little bit confused by something like nest. I would have thought there was just a formula for the derivative here. I mean, a formula in a generalized sense of the term formula. That is, I would have expected we could just derive. Am I wrong here?
See, there are cases where we can just derive it. Exactly.
Yeah.
That's what I was saying.
Rob, what does your code do for your differentiator do for nest?
Well, nest, by the time I get to my differentiation, nest is, I believe, already been unrolled into a loop.
Yeah, that's
and so
correct.
it just handles the loop.
Yes, but
by handling the loop, you mean by a code graph?
Yeah, it's a code graph with the loop, and so see, this is a perfect example. So if you had an n there, which was large, if you actually compute the nth derivative, it's a disaster, right? But if you compute one of these forward or reverse things, it's quite efficient because it doesn't have to do that whole big expression as well to get the nth derivative.
Okay, so I have a suggestion here. Okay, so I'm wondering whether for a bunch of our functions, I'm wondering whether we could just, I mean, we've never tried doing this, whether we can, okay, actually, no, another way to think about this. Okay, so you've got a code graph. Many of our functions imply a certain piece of a code graph, correct? So my question is, first of all, do we have a nice symbolic way to represent the code graph? And second of all, I mean, so there are several pieces to this. Can we represent the code graph symbolically? The code graph is not that different from neural nets and recursive neural nets and recurrent neural nets and all this kind of thing, if I'm not mistaken. Is that correct? That is the code graph, right?
Generic code is more expressive. You have more statements, you have branches, ifs, and stuff like that. But essentially,
for what? I'm sorry.
I mean, no. For the code graph, there's no if. It's just going to be one graph. Huh?
There's no loops. There's just it's just a graph with no edges.
Right.
But the question was, can we represent generic programs with graphs?
No. It's execution trace, I think.
Okay, so the trace is always an acyclic graph. Yes, of course.
And it's a reducible graph with what the compiler only produces reducible graphs.
So, this old function trace, which let me run this one, for example, here.
Turn the 20 into something a bit smaller.
I know. I was going to.
Right.
Okay. This function, developed in 1991, was an attempt to represent. Okay, so an interesting sub-project is to make this into a graph.
See, what would be more useful would be to generate the graph that's for the lambda function, the code graph, and then to animate, visualize the flow of data through that.
Fine, but I mean, but this is an example. Okay, so this trace here is an example of something. If we turn this into a graph, my guess is that see, this case is awkward. This recursive case is awkward because it has an arbitrary length. But imagine there was another parameter here. We could take this thing and we could say, let's hollow out this thing and feed our other parameter through this same execution trace graph, if that makes sense. Right, so in other words, if we can represent this by a graph, we can take, and then once we have this graph, am I correct that it's rather straightforward to do the differentiation?
Yes, it's relatively straightforward.
I mean, I must add, if there's only one output, yeah, it's straightforward, just by propagation. In the case where you want the Jacobian and you have like, I don't know, 200 input and 50 output, and if it's completed graph, there's actually a very specific way to apply the chain rule. There's optimal way that is hard to find. It's actually an NP hard problem to find the optimal way to combine the derivatives to obtain the Jacobian. Anyway,
well, we actually have code in the kernel, surprisingly enough, with this numerical function that uses it. It doesn't solve the NP complete problem, but what it does is it does a dependency thing and tries to do as few computations as possible. So
right.
It's not optimal, but it's close to optimal.
Right.
And this was used for our finite difference stuff before.
Well, okay, so listen, I mean, there's clearly a bunch of interesting things here. Richard on a live stream is pointing out all kinds of things about, is noticing multi-way neural nets, which, yes, are an interesting thing, which I have thought about a bit. And the question of people are also pushing gradient through Runge-Kutta solvers using adjoint methods for neural ODEs.
Yep. See, that's part of the reason I came up with this design. So we need to have a design for that concept, and then we could use adjoint sensitivity for ND solve and parametric ND solve and get these gradients. That's one of the things we could get out of a good design.
Right. Well, I think we're going to get a good design. It's going to take us another hour or two. I mean, basically, this is the thing to be thinking about: is what do we do to make a function? And let me parameterize what I think we have to do. Thing number one, we need a design for this thing, which I think, as I said, would be the general case is case 0 here. Thing number two, we then have to be able to take pieces of code where we essentially generate something very analogous to the output of trace, right? And essentially what will happen is the output of trace will have a particular form, but the numbers will change, the structure will stay the same. That's the case where we can do automatic differentiation, if I'm not mistaken. Is that correct? I mean, like loop lengths, how do we deal with the change of loop length? Guys?
In automatic differentiation?
Yep.
Well, there's no problem because it's once the program has been executed. So.
No, I understand. But if one of the parameters affects the length of the loop, how does that work? In other words, if you can't do that, right? If the loop has n elements And that thing that I gave before, awkwardly, which had a flaw in the nest.
Yes. Well,
right?
as I mentioned,
I think you're out of luck in that case.
You are out of luck because there are cases. So automatic differentiation can typically handle one point of non-differentiability.
I wonder
whether disaster and it gets
the
wrong.
floor is fine, huh? The floor is fine because it's just around a x. If x 2.3 around 2.3, it's just 2.
No,
so,
I know that, but
no.
Etienne, the problem is in this thing where you're basically tweaking a code graph. Your code graph has a different structure depending on the value of x, and I don't think you can handle that.
Well, see, so that's an integer valued thing, floor. So basically, its derivative is 0 almost everywhere, right?
Exactly.
So,
all right, okay,
and the thing is,
I don't think it's a problem.
I don't think it's
it is a problem. It is a problem.
I don't think it's going to work, but it doesn't matter.
But
let me give my outline for how we should do this. Okay, so my claim is that conceptually, we got this function on the outside. We say, okay, great. Now we've got the inner function. We evaluate it sort of semi-symbolically to produce an execution trace. That execution trace, I don't know exactly what the type inference pruning of that execution trace is. I would not be surprised if we couldn't use our theorem prover to do a few things here to simplify that execution trace. But in any case, but be that as it may, then given the execution trace, there are essentially symbolic parameter points, you could call them, in the execution trace that are the places that you can wiggle to get the derivatives, if that makes sense, right? And the outer function is defining, this execution trace probably doesn't care. It may have, 3 input dimensions, 5 output dimensions. That means there are, lots of parameters you can wiggle in here. But you only are interested in a particular, you're only interested in whatever the projection is for case 1 and 2 here. So then my claim is that it then becomes, so if you can write this, and it may be really straightforward. It may be really straightforward, given that we have a symbolic structure from trace to create this code graph, basically, that then allows us, maybe we don't even have to invent all of this combinator stuff. Maybe it already exists just by looking at the execution trace here. I'm not sure. Requires thought. Okay, I think I need to go because I'm late for something else. Okay, this is very helpful. I never really dug in properly to I should have done years ago to this question, because this is actually, I think that, I think we're going to be able to do something really good here. And my guess is that the main role of the compiler will be in essentially simplifying this general symbolic representation of the execution, graph. That would be my guess. And it requires, plus it may be, my guess also is that we actually just need to derive derivatives of a bunch of our functions.
Yes, I think we need to do that.
Right.
If I talk from language implementations for them, then we could derive them with the compiler.
No, I don't think we want to do that. I think we want to get a nice optimized piece of code that is the derivative of a nest, or it is the derivative of something more obscure. But yes, that problem is not that different from seeing how to compile that function down to what ends up as low-level code.
Yeah.
But it isn't quite the same thing, because what we want here, it's a little funny, because look, I could imagine like our old line calculus folk actually coming up with formulae for the derivatives of a bunch of our functional programming constructs, okay, as formulas, basically. And those formulas may contain other functional programming constructs that are quite compact and quite efficient and even quite readable. But you could also write everything in terms of low-level, loops and things like this that the compiler would want to generate because that's what the low-level machine code stuff is going to be.
The compiler's generating, they're actually, they look like loops, but they're really function calls, you see.
Well, that may be, but the fact is, I'm saying there's two different objectives here.
Function calls. So
One objective, what?
Fine, yeah, go.
One objective would be take a piece of functional code and make an actual human readable derivative for it. That may not be possible, I don't know. It may be that it takes only that just like that we could have a nest prime function, just like, you know, we have a function zeta prime that's a derivative of the zeta function, which has its own code that does things, right? I mean, I'm sure if I do numerical value, that'll just give a value, right? So we could imagine something very bizarre where we have essentially a nest prime. Do you get what I'm saying? Where, in other words, we're taking our functional programming constructs and we are defining, you know, either explicitly represented or formal derivatives of them symbolically. See what I'm saying?
Yep.
Sure.
I think this is the way to think about this. All right, I gotta go. All right, thanks guys, and thanks to folks on the live stream. A bunch of interesting comments there.